There's not really any new physics in this video. We're going to look at the motion of charged particles in electric fields, and we've already looked at forces on particles due to electric fields. So this is basically looking at a couple of applications, and they're not too bad. So we defined originally the electric field as the electric force felt on a charge per unit charge, so F over Q. If we rearrange that, we get that the force is Q times the electric field. And if it's the only force acting on the particle, or the only significant one anyway, which is often the case, we'll see that gravity is typically so small compared to the electric force that we can ignore it. So we can set that equal to ma by Newton's second law. And if we solve for acceleration, we can find that in terms of the electric field, the charge, and the mass of the particle. And then we might have some kinematic calculations to do with our acceleration found in this way. So two examples. First one, we have parallel plates that are charged, and we are releasing an electron from the negative plate. It will be repelled by the negative plate and attracted by the positive one. Or we can just think about it in terms of the electric field. The electric field is pointing that way, and that's the direction that positive charges will feel a force. So a negative charge is going to go the other way. And we've got this little chunk cut out of our positive plate here just so we can send our electron flying and use it for whatever experiment we want. We have some details here: the mass of the electron, the magnitude of the electric field, the separation of the plates, and we want to know the speed at which our electron leaves this hole, assuming that it started out with an initial velocity of 0. So we can apply that equation that I just showed you to find the acceleration, and then do a pretty simple kinematic calculation. So the acceleration is Q, the charge, times the electric field over the mass of the electron. The charge in this case is the elementary charge, 1.6 times 10 to the negative 19th. The electric field is given up here, 2 times 10 to the 4th. And then we just divide that by the mass of an electron, which is also nicely given for us here. And all of that works out to be, yeah, that's my negative sign there, an acceleration of 3.5126 times 10 to the 15th. So you'll see with charged particles, these forces can be relatively large with incredibly small masses, so we get huge accelerations, and that makes it easier for particle accelerators and whatnot. Now, if we know the acceleration and we know the initial velocity, and we're going to try to find the final velocity, we're also given the distance that it moves. We want to use v squared equals v naught squared plus 2a delta x. Now this equation was derived assuming constant acceleration, so we got to mentally check, is that okay to use that in this situation? Well, the electric field is constant between the plates here, and if the electric field is constant, that means the force and the acceleration are constant. So yes, it's okay to use that in this situation. If you have a charge, maybe a charged particle, and then another smaller charged particle or something that is being attracted to it, in that case, the electric field due to that charge is not uniform, so you would not be able to assume constant acceleration. Alright, so plugging into this equation, initial velocity is 0. Our final velocity is going to be the square root of 2 times our big fat acceleration times 10 to the 15th times the delta x, which is 1.5 centimeters, 0.015 meters. And all of that works out to be 1.0 times 10 to the 7th meters per second. So we can accelerate electrons quite quickly. Just to comment on units, Q here was measured in coulombs. The electric field was newtons per coulomb. This was kilograms, so the coulombs cancel out, and we have newtons per kilogram, and a newton is a kilogram meter per second squared over kilograms, so kilograms go away, and we do get acceleration out of that. Second part of the question, show that the gravitational force can be ignored. Well, there's a couple of ways you can look at this. For one, we can just look at the acceleration due to the electric field. It's 10 to the 15th, whereas the acceleration due to gravity is just g, 9.8. So that is basically enough evidence to say that is insignificant compared to this, and we can ignore it. Another way you could look at that is to say, well, how do these forces compare? The electric force, which is QE, works out to be 3.2 times 10 to the negative 15th newtons, which is not all that large, but since we have such a small mass, it still gives us a big acceleration. The gravitational force, which is mg, works out to be 8.9 times 10 to the negative 30th, which is much, much, much smaller than this. Even though that is small, that's incredibly smaller, 15 orders of magnitude smaller. All right, one more example. This time we've got our plates this way, and our particle comes in with some initial velocity horizontally, such that the electric field is going to deflect it down. Again, we've got an electron, so it gets deflected in the opposite direction of the electric field, and we want an equation to describe its path while it's in the electric field. We can ignore gravity for the reasons we just talked about. So we can use our kinematic equations. In the y direction, we do have constant downward acceleration, and so we can use y equals v naught t plus 1/2 at squared. Now this is the initial velocity in the y direction, and since it came in horizontally, this is 0. In the x direction, there is no force acting horizontally, so we just have our what we call the initial velocity here times time. And this is one way we could describe the motion of the particle. But if we want to parameterize or anti-parameterize these equations, we can plug in, solve this guy for t and plug it in over here. So t is x over v naught, so I can get y equals 1/2 times my acceleration x squared over v naught squared. And if I want to write this acceleration in terms of the E field and the charge and all of that like we did earlier, then I'm going to get 1/2. I'm going to go ahead and put a negative here to indicate that that acceleration is downward from the perspective we're looking at. Q times the magnitude of the electric field over mass. So this whole thing is my acceleration, x squared over v naught squared. And then if we just want to clean things up a bit, we could plug in e, lowercase e, for q here. So we're going to have negative little e times big E all over 2m times v naught squared. So all of this stuff is constant, and then all of that times x squared. So we will have parabolic motion, just like projectile motion. So there is our equation of motion. See you next time.